So, once again, welcome one and all. In this lecture, we will discuss one more characteristic for a good estimator, which is sufficiency. Okay. So, here, this is the first thing about sufficiency. And actually, this is the basic definition of sufficient estimator. So here it is mentioned that T, which is a function of sample observations, x1, x2, xn, it is an estimator of parameter theta, okay, based upon the sample size n from the population density fx theta. So this fx theta, we know this is the density function, okay, or probability distribution function of the population, such that the conditional distribution of these sample observation, the conditional distribution or the conditional probability distribution of these sample observation given the value of t, okay, if this conditional distribution, okay, or conditional probability distribution given the value of t, okay, if it is independent of theta, then we say that T is sufficient estimator for the unknown parameter theta. So mathematically, we write that if this conditional probability, okay, so conditional probability that given the values of sample observations, okay, sorry, not given the value of T, then further the conditional distribution of these sample observations, the conditional distribution of these sample observation, it is independent of the unknown parameter theta, then T is sufficient for the theta. Now, this definition, it is bit beyond our present scope in order to study sufficiency. I repeat, in order to study sufficiency, this definition, it is bit beyond our scope of this present lecture series. Otherwise, if time is there, okay, and if a demand is there, I would like to discuss the sufficiency with the help of this basic definition also, okay. Yeah, it is actually very closely related to our real life situation. It can be explained through the real life situation. But at present, we will not discuss sufficiency according to this definition. Rather, we will discuss the this sufficiency according to this necessary and sufficient condition. Okay, so here this necessary and sufficient condition for sufficient estimator, it is known as factorization theorem. It is known as factorization theorem due to name n. Okay, so in this one, actually, we will use L. Okay, this L, this is nothing but the likelihood function. Okay, here it is mentioned. It is mentioned as a joint density function. So obviously, because this L was the product of fxi theta. Okay, so recall back that this was our likelihood function, product of these I1 to n. So obviously, what is this fxi theta? It is the density function. Okay, and here we have the product. We have the product of n values. We have the product of, means pi product of n values of this function. Okay, obviously these n values, they are nothing but the values of f at first sample observation into or multiplied by this f, the value of f at second sample observation going on. So basically this L is f x1 theta into f at x2 theta going on up to f at x and theta. Okay, so that's why this is what we call joint. Okay, joint means it is made up of more than one values. Okay, so we will use this L, and I have already discussed many questions on this based upon this ML, this likelihood function. So it is strongly suggested that before going through this lecture on sufficient estimator, one must go through the lecture on MLE, the maximum likelihood estimation. Okay, because some results from that lecture I will be directly using here. Okay, so please go through that lecture. Now, this, wait. So now this theorem, it says that if I can factorize my this likelihood function or joint density function into this form, okay, into two functions, G and H, into two functions, G and H, where G, it depends upon the unknown parameter theta, okay, it must depend upon the unknown parameter theta, and it should depend upon X. Actually, what here X will represent sample observations. Okay, so here you can see this L, it depends upon sample observations and this parameter, unknown parameter theta. So G, actually, it should be a function of theta. It should also be a function of X, the sample observations. Okay. But it should be a function of sample observations, but only through a specific function T. I repeat, this G, it should be a function of sample observations, but only through or only via, okay, some specific function T. And this T, it will be further the function of these sample observations. Okay. In other words, in G, in this function G function, if sample observations are present, okay, if in G, the sample observations X, they are present, then they should be present as a part of single function T. They should be present as a part of single function T. In other words, the sample observations, it should not be present in G in any other form. I repeat, the sample observations in G, they should be present only as a part of single function T. Okay. Now, what is this H function? Actually, this H function, it should be a function of only sample observations. It should be a function of only sample observations, or here Hx, it should be independent of theta. Okay, so at present, this definition, it is not that fully understandable. I can very well feel what you are feeling for right now. Because when I studied this for the first time, so I was not fully feeling fully connected, okay, or confident. So wait for the questions. If when we are discussing the questions, each and every term will become crystal clear. Okay. Now here some remarks. First one, that if our hx, if it is k, where k is what? It is some constant, means hx, it is a constant function of x. Then also hx satisfies the condition that hx is independent of theta. Okay. Okay. So this is the first remark that this we will use. That if hx, it is equal to some constant function of x, then again we will say that hx is independent of theta. Okay. Actually, once again, I told you that this Hx, it should be a function of sample observations only. It should be a function of sample observation X only. So obviously this function, we can define it as a constant function of X. We can define it as a constant function of sample observation. We can define this H as the constant function of sample observation. Okay. Now, it should be clearly understood that a function independent of theta, actually here we are actually, once again, we are talking about hx, okay? We not only mean, we not only mean that it doesn't involve theta, but we also mean that its domain should not also involve theta, okay? Means this h, okay, this function h, it should not have any theta, the unknown parameter theta, but also its domain should not have any theta. For example, if you look at this function fx equal to 1 upon 2a, Once again, it is a constant function, fx equal to 1 upon 2a, but look at its domain. Domain, it is between, domain means the values of x from the set from where this x is draws its values, or x can have its values. Now, the domain of this function f, it is depending upon theta. You can very well say, you can very well see that this x, it is lying between a minus theta to a plus theta. Okay, means this domain, okay, the domain of this function. Okay, domain means the set from where this x, the x is taking its values, it is depending upon theta. So this function, it is depending upon theta. Why? Because its domain, it is involving theta. Okay. So then one more thing here. This t means in G, I told you about this t. Now, if theta has only one component, if theta is only one component, so this t, the estimator, okay. Actually, the definition is, this theorem is, if I can factorize my L in this way, if I can factorize my L in this way, okay, then I will say this Tx, okay, this is sufficient estimator for theta. This Tx, okay, this is sufficient estimator for theta. Now, if theta has single component, it has single component, then Tx, it will also have single component. And if theta has, say, two components, say theta 1, theta 2, then this Tx, obviously, it will also have two components, T1x and T2x. Okay, where T1x, it will be sufficient estimator for theta 1, T2x, it will be sufficient estimator for theta 2. And it will go on like this, that if theta has, say, three components, even this t, okay, which will be sufficient estimator for theta, even it will have three components. Okay, so this thing is there. So if we can factorize L as G into a product of two functions G and H, if we can factorize our likelihood function into the product of two functions G and H, where G, it is depending upon theta, also it is depending upon the sample observations, but only through T, and H, this is the function of sample observations. Okay. So if we can factorize L in this way, then we will say this Tx, we will say this Tx, it is sufficient estimator for theta. Okay. And this Hx, it can be constant function of x, and moreover the domain of this x means our sample here, actually x is, once again, it represents sample observations, means the sample observations, they should not be dependent upon theta. Okay, so sample observations, they should not be dependent upon the unknown parameter theta. Okay, now let us see example to understand all these things explicitly. Uh, which of the following is the sufficient estimator for this parameter theta of a population which is having density function? It is this one. Okay. Now, what is our L? It is pi product fxi theta. Okay. And this is now pi, and it is theta xi, theta minus 1, I1 to n. Okay. So this is theta x1, theta minus 1, theta x2, theta minus 1, so on, theta xn, theta minus 1. Okay. So this is nothing but our density function of the population from which this sample is being taken, okay, or drawn. So now this product is nothing but this. Now this is nothing but theta raised to power n. Why? Theta into theta, so on up to this theta n times. Now x1, this is raised to power theta. You can see here it is x1 raised to power theta into even x2, even it is raised to power theta. So here what should I write? X2, which is raised to power theta. Going on, next term it will be x3 raised to power theta. So going on up to xn raised to power theta, you can see. And x1 raised to power minus 1. Okay, x1 raised to power minus 1 into x2 raised to power minus 1. Okay, so on xn raised to power minus 1. Okay, so this is now theta raised to power n, and this product pi xi, the product of the sample observation. Okay, so what is this? The product of the sample observation raised to power theta. And once again, this thing, it is actually the product of again sample observations. Okay, but here I have taken it into the denominator. I have taken here it is in numerator. It is raised to power minus 1. So in denominator, it is raised to power plus 1. So this is our L. Now, this L, I can compare with this g theta tx into hx. This L, I can compare with this g and h, where what is my g? What is my g function? It is nothing but this function. Okay, obviously, this it is depending upon theta. Yes, it is depending upon theta, the unknown parameter. Now look, this g. Okay, so here this is our g function, g theta tx. Now this g function, this one, how it is depending upon x, the sample observation. I repeat, look or observe, notice that how this function g, it is depending upon sample observation. So it is depending upon sample observation through which function, through what and form? It is the pi xi. I repeat, g, it depends upon sample observations through pi xi. Okay, so this pi xi, the product of sample observation, it will become our px, the function of sample observation. And what is this hx? Obviously, this function, it is our hx, which is totally, purely a function of sample observation. And moreover, here, our x means our sample observations, the domain of h. I repeat, this x, which represents sample observation or domain of h, okay, it is independent of theta because it is between 0 to 1. Okay, it is between 0 to 1. It doesn't depend upon theta. So here, uh, this is our so we this L, it is satisfying the Neyman criteria. Okay, so we will declare now that this Tx, okay, which is nothing but this product, it is sufficient estimator for theta. So here I write that this pi x, the product pi xi is a sufficient estimator for theta. Okay, because it is, we can say, the factorization theorem is satisfied. The criteria, the factorization theorem, a criteria is satisfied. Okay, so that's why this is sufficient estimator for theta. So, what we have proved that if we are drawing a sample, okay, from a population whose PDF is this, okay, then the product of the sample observations, the product of the sample observation, it will be sufficient estimator for the unknown parameter theta. Now, once again, we have a sample which is of size n, and it is from a population with whose density function is here. We have to find the sufficient estimator for theta. Now, once again, if you look carefully, our x, the sample observations, they are independent of theta. So, what is L now? It is pi fxi theta. Okay. One remark here. Just wait, please. Mm, yeah. Actually, here, if the domain of H, okay, if the domain of H means X, if they depend upon theta, okay, just like this function, if they depend upon theta, then we cannot use this factorization theorem due to name n. Then we will not use this factorization theorem due to name n. Obviously, why? Because if the domain of H, it depends upon theta, then obviously this condition that Hx is independent of theta, it will not be satisfied. So if the domain is dependent upon theta or Hx is dependent upon theta, okay, if the domain of H, whether it is dependent upon theta or Hx is dependent upon theta, I repeat that whether the domain of H or H itself, if any of these or both, they depend upon theta, then we can't use factorization theorem to find the sufficient estimator, actually factorization theorem due to name n. Then we have one more criteria that is also a factorization theorem, but that is Fisher name n criteria. That is Fisher name n criteria. Okay. So at present, we will not discuss that criteria. So we are having only this name and criteria at present. Now here, the L now. So what is this now? 1 by theta E minus xi upon theta. Then 1 by theta E minus, sorry, it should not be xi, it should be x1. So mm, x1. Here it should be minus x2 raised to power theta and 1 by theta e minus xn upon theta. Okay, so this is now 1 by theta raised to power n. You can see here this term is multiplied n times, and e raised to power what? E raised to power, actually, if you take common minus 1 by theta, you can see here 1 by theta we can take common. Remaining will be summation xi. The remaining will be summation because x1 plus x2 plus xn, because the base is same. E base is same. So that's why we will have this. Okay. So now this I can write that, okay. Wait. So how should I write this? Mm, yeah. So this is the thing. And here I can write that this is g theta dx into hx. Here, what is this g function? Actually, this whole, it is g function. And what is our hx? It is 1. Hx is 1. Okay. Actually, if you look carefully in this one, can you find any function which is totally or only, okay, which is only the function of sample observations? In this one, can you find a expression or a function? Can you find a expression or a function which is purely or only the function of sample observation? No. Actually, this one, it is depending upon theta. Even this one, it is depending upon theta. But it is depending upon theta as well as on the sample observation. So that's why here we can assume that our hx is 1. Moreover, this whole expression, as I have already pointed, so this is our g function. This is our function g because it is depending upon theta. Surely it is depending upon theta. And it is also depending upon x, the sample observations, but it is depending upon the sample observations, but only through this function, summation xi. I repeat that this function uh, g, okay, it is depending upon, so it is depending upon the parameter theta, okay, Also, it is depending upon x, the sample observations, but only through this function. So this summation xi, it is going to be our tx. So now here you will write in your exam, okay, that since the criteria due to factorization theorem, since it is satisfied, okay, so that's why this summation xi equal to tx, means sum of the sample observations. Okay, in this case, so this one, it will be the sufficient estimator for theta. So summation xi, so this implies that equal to tx. Okay, the sum of sample observation is sufficient estimator for theta. Okay, one thing here. My major focus is on explaining the things. But in your exam, you must write the things properly. Okay. So here we have a random sample of size n of a population having Bernoulli distribution with parameter p. Obviously, what is this p? It is the probability of success. Okay, we have to find the sufficient estimator for p. Now, many things in this question. For example, what is Bernoulli distribution? What is the meaning of p? Okay, or even here what will be the likelihood function. All these things, they are either in lecture number 1 of this series, or in the lecture number 5. So do watch those lectures if you really want to feel connected with the terms which are being used here. Now, what is our L once again? It will be product of fxi theta. So here this is nothing but p raised to power xi 1 minus p 1 minus xi. So I 1 to n. So this is now p summation xi 1 minus p n minus summation xi. Okay, so this how this is equal to this. This is in the previous lecture. Now this thing I can write. So here, what is our theta? Theta is nothing but p. The unknown parameter theta is p. So this is now g theta tx into hx. This is means this expression, it is comparable with this, where what is our hx? Hx is nothing but once again 1. Why? Because in this expression, we are in this expression we are unable to find a function which is totally a function which is purely only. Okay, so in this expression, we are unable to find a function which is only a function of sample observations. Okay, and moreover, this expression, actually it is a function of p, the parameter. Okay, and it is a function of sample observation. It is a function of sample observation. So this is our g. Here, theta, instead of theta, you may write that this is GPTX. Okay, GPTX. So this is our, actually in exam, you will write that GPTX. Okay, so this is P summation xi 1 minus P and minus summation xi. Okay. And now here you see that this G, it is depending upon our parameter P. It is also depending upon sample observations, but only through a single function, summation xi. This G, it is depending upon the sample observations, but only through a single function, summation xi. So this summation xi, the sum of the sample observation, this is going to be our Tx, and this Tx, it is the sufficient estimator for P. Okay. Since the factorization theorem criteria is being satisfied. So here we have a random sample from a population which is having Poisson distribution whose parameter is lambda. we have to find the sufficient estimator for lambda. So L is nothing but pi fxi theta. What is theta here? Lambda. So this is actually E minus lambda into lambda raised to power xi upon xi factorial I1 to n. So this is actually E minus n lambda, E minus n lambda into lambda raised to power summation xi and divide by this product xi factorial. Okay, so this is our L now. So, so this is, can I compare with g theta tx into hx? Yes, I can compare. Now, what is this g theta? Actually, this is e minus n lambda into lambda raised to power summation xi and into 1 by this product xi factorial. Okay, I1 to n. So what is this function? This function over g, okay, because it is depending upon theta, the parameter, and what is theta here? Lambda. The theta is lambda here. So it is depending upon lambda, and it is also depending upon the sample observations, okay, but only through this function, summation xi. And what is this function now? This function is our h function, okay. H function which is only a function of sample observations. Actually, even in this question, what is your this the sample observations? Actually, they are independent of lambda. If you have ever observed in Poisson distribution, the x, the domain, it is actually 0, 1, the random variable basically, 0, 1, 2, going on up to, okay, infinity. So even it is independent of lambda. Even in the previous question, our x was either 0 or 1. Means our sample observations, they can either take the value 0 or 1. And even both these values, they are independent of p. Okay. So that's why in these questions, we are applying the factorization theorem due to Neyman. So now here, what is this g function? G lambda tx. Okay. This is nothing but e minus n lambda into lambda, lambda raised to power summation xi. And what is this h function? It is nothing but pi xi factorial. Okay. So hence by factorization theorem, here I will write due to Neyman. Okay. This summation xi, okay, this is sufficient estimator for the parameter lambda. So now we have a random sample from normal population, and we have to find the sufficient estimator for both two parameters mu and sigma square. So first of all, here our theta, the unknown parameter theta, it has two components. One is mu and another is sigma square. So this is theta 1 and theta 2. So our Tx, the sufficient estimator for theta, our Tx, the sufficient estimator of theta, even it will have two components. One will be T1x, the another will be, just wait. Yeah, the T2x. Where what will be T1? It will be the sufficient estimator for mu, okay, which is theta 1, which will be theta 1. And T2, it will be sufficient estimator for sigma square or theta 2. Now, the L now, the likelihood function, it is product fxi theta. Obviously, I1 to n. So this is now 1 by sigma root 2 pi. 1 by sigma root 2 pi e minus e raised to power minus half x minus mu upon sigma square. Okay. So whole square. So this is the PDF of normal distribution. Okay. And now this is nothing but 1 by sigma root 2 pi and whole raised to power n and e raised to power minus 2 sigma square and summation of xi minus mu whole square. Okay. Now this thing is 1 by sigma root 2 pi. Okay, this E minus 1 by 2 sigma square. So this is summation. Actually, now xi square plus mu square and minus 2xi into mu. Okay, so actually, this is a minus b whole square. So a square plus b square minus 2ab. Nothing but that. Now, from this one means this. Product to this means from this step to this step. Actually, this is it has been proved in the lecture on MLE. Okay, please do watch. So now this is yeah. So now this is 1 by sorry here it should be whole raised to power and so this is now 1 by sigma and this thing and here and e raised to power minus 2 sigma square summation xi square. Okay, then summation mu square, then minus actually summation of 2xi and mu. Okay, so this thing. So summation of xi square, summation of mu square, summation of this term means mu, summation over every term. And now this is obviously I1 to n. Okay. So this is 1 by and e minus and now summation xi square and plus n mu square and mu square because mu square is a constant and we are adding a constant. Here we are adding a constant n times and minus here it is 2 mu and summation xi. Okay, because this 2 and mu they are constant with respect to this summation. This summation is with respect to y. Okay, so that's why they can be 2 into mu, they can be taken outside this summation. Okay. Now, this L I can compare with g theta tx, okay, and into hx. And once again, here in this expression, in this whole expression, we are unable to find in this whole expression of L, okay, this one. So we are unable to find a single function, okay, which is a function of sample observations only, x size only, okay. And moreover, this whole function, actually it is a function of theta, the parameter theta. Actually, theta has two components. What two components? Sigma square and mu. Means this whole function, it is depending upon, the whole function is depending upon mu and sigma square. Also, this function g, this whole, actually, what is your g function? This g theta tx. So this is actually 1 by sigma root 2 pi and then this n here and e minus 2 sigma square and summation means I will not rewrite here, but in exam you will write these. And what is your hx? Obviously hx is 1. And if you have observed by now, if in L we are unable to find a function which is purely a function of sample observations, then we take hx as 1. Okay. So this whole expression, it is a function of sigma and mu square. You can very well see theta, this whole expression, g function. It is a function of mu. It is depending upon mu and sigma square over theta. And now this whole g, this function, it is also depending upon x size, sample observations. Okay, but only through two functions. One function is here summation xi square, and another function is this summation xi. Okay, so the here theta has two components, mu and sigma square. And our T, even it has two components. One is actually summation xi and the another is summation xi square. Means this summation xi, it is T1x, and this summation xi square, it is T2x. Okay. So here now we will write in exam, you will write that this summation xi, it is the sufficient estimator for mu, and summation xi square, it is the sufficient estimator for sigma square. Okay, since the factorization criteria due to Neyman has been satisfied, so here you will write, so this implies summation xi, okay, which is our T1x, is a sufficient estimator for mu, okay, and summation xi square, summation xi square, which is T2x. So this is sufficient estimator for sigma square, okay. Now here, one remark which usually the authors or other teachers they miss, that how we come to know that this T1 means summation xi, that it is sufficient estimator for mu. Why it is not sufficient estimator for sigma square? Okay, so here, suppose I have the sample observation. So x1, say it is equal to -3, x2, it is equal to 0, and x3, suppose equal to 1. Okay, so what is my point? That how we come to know that this T1x, summation xi, it is the sufficient estimator for mu. Why it is not a sufficient estimator for sigma square? Okay. So for that, I have a sample, okay, sample observation of three observations. Now, what will be summation xi? Means if you add these, it will be -2. Now this -2, it can't be the sufficient estimator for sigma square. This -2, it can't be summation xi -2. It can't be the sufficient estimator for sigma square. Why? Because sigma square is a variance which is never negative. Okay, means this summation xi, this value of summation xi, it can't act as this value of summation xi, it can't act as this estimated value, sufficient estimated value for sigma square. But if you take this summation xi square, so what will be that? It will be 3 square 9 plus 0 square plus 1 square, that will be 10. Yes, there is no issue. So this 10, it will act as, or it will serve as, this summation xi square equal to 10. It will act as, or it will serve the purpose of the sufficient estimated value of sigma square. Okay. Now here we have a sample of size n from population which is having gamma distribution. So directly, what is L? Actually, we have to find the sufficient estimator for alpha and beta. So L is actually pi fxi. Theta, actually you may write alpha beta. Okay, so this is now uh, pi 1 by gamma of alpha and beta raised to power alpha, and x raised to power alpha minus 1 into minus x by beta. Okay, so here instead of x, I should have xi. So even here, I should have xi. Please wait. Yeah. So minus xi. Actually, this is the PDF of gamma distribution whose parameters are alpha and beta. Okay, so I1, 2, and now what is this? It will be 1 by gamma alpha, beta raised to power alpha, and whole n. Okay, and here it will be product pi xi, okay, and raised to power alpha, and once again pi xi. Here it is, this one. Actually, I'm talking about this term. And what about this term? It will be E minus summation xi upon beta. Okay, how this is equal to this? Actually, you will do the steps that we have done in the lecture of MLE. Means you will write these values. First value at I1. Okay, means at x1 into the value of this whole expression at I2, means at x2 going on up to IN. Okay, and if you simplify, obviously you will get nothing but this expression. Okay, so now this expression, if we can write that it is gamma alpha, beta alpha, and n here, and pi xi alpha. Here it will be raised to power alpha. Uh, yeah. So alpha and e raised to power summation xi upon beta into what? Into this product xi. So this is now comparable with g theta dx into hx. Where, what is this hx? Actually, you will write in exam where hx is nothing but this. Okay. So where hx, which is a function of sample observation only. It is 1 upon pi xi, the product of the sample observation. And what is this g theta? Okay, here g theta tx. Actually, even here, theta is having two components, okay, the alpha and beta. It is clearly mentioned that the alpha and beta, they are the parameters of this gamma distribution, which the population is following. Okay. So theta, so even our t, it will have two components. One will be t1x and another will be t2x. Okay. So what is this g theta tx? This whole expression 1 by gamma alpha. Okay. Beta alpha and this pi xi whole raised to power alpha and e raised to power minus summation xi upon beta. So now here, actually, in this G, you can see this G, it is depending upon theta, the parameter, alpha and beta. So here, this G, it is depending upon theta, the parameter theta, which is means depending upon alpha and beta. And it is also depending upon the sample observations, but either through this function pi xi or through this function summation xi. Okay, so here, what is this T1x? Actually, T1x, it will be pi xi, the product of the sample observations. Okay, so how I can say that this T1, that this T1, that this is pi xi, which is sufficient estimator for alpha. Why not it is sufficient estimator for beta? If you look carefully, this pi xi, it is connected with alpha. It is associated with alpha. And this summation xi, it is associated with beta. Okay. So T1x, this is sufficient estimator, mean this product of the sample observation is a sufficient estimator for alpha. And T2x, which is summation xi, it is sufficient estimator for beta. Okay. So hence this the result. Now, it is not necessary that every population, okay, it admits or it has a sufficient estimator. So, for example, we have a random sample from a population which is having a Cauchy distribution. Actually, this one, it is the PDF of Cauchy distribution. Okay, and what's the parameter here? Theta. So it doesn't have any sufficient estimator. Okay, so L is nothing but this product. So I will directly write that it is pi 1 plus x minus xi minus theta whole square. Okay, so I 1 to n, and this is now 1 by pi raised to power n, and here once again it is product, will be product of this term 1 plus xi minus theta whole square, and I 1 to n. And obviously, this we cannot compare, this expression we cannot compare or write as g theta tx into hx. Okay, so this expression, it is not comparable with this expression. You can very well see they are here. We don't have any g basically. We don't have any g, which is a function of parameter theta. Okay, so what is the parameter theta? Theta is here. Okay, which is also a function of x, the sample observations, but only through single entity, the single function of x. How someone ways, if you simplify further, so actually it will be product when you are giving the product, or why not even before the product, it is 1 upon actually xi square, okay, plus theta square minus 2xi theta. You can see very well, okay, this one. So I 1 to n. Okay, so you can see here the a minus b whole square. So now in this one, if I take it as g, suppose I take it as g. So in this g, these sample observations, they are present either as this xi squares, and they are present as xi also. Okay, so here this g, it is not a function of sample observations, but only through single function of xi. So that's why here theta does not have any sufficient estimator. In other words, theta doesn't admit any sufficient estimator. Okay, so thank you everyone.